Students, hi, this is Mr. Bobenrieth. In this video, I'm going to walk through a sample incline plane practice problem. And this is a class of, or a type of problem that often appears in physics. And it helps us kind of understand more deeply how we can use the tools we've been studying this year and Newton's laws to attack a problem like this. So I'm just going to read the problem out loud, and then we're going to go walk through it together. So it says a box of mass 4.0 kilograms accelerates down a friction-filled ramp to the right. The ramp is elevated above the horizontal by an angle of 37.0 degrees. The coefficient of dynamic friction between the box and ramp surface is 0.25. Assume air resistance is negligible and G equals 10.0 meters per second squared. It's asking us to do 6 things here. 1, sketch the scenario. B, drop a free body diagram. C, complete a forces table. D is determine the size of the normal force. E is determine the size of the dynamic friction force. And F is determine the acceleration of the box. By the way, I just kind of previewed the problem, and that's a really good idea when you start, before you just jump into a problem full force. Read through it entirely, see what stands out to you, and then kind of go back and read it again more deeply. Okay, so let's start in. It says A, sketch the scenario, including establishing a set of coordinate axes. So I've actually already started this a little bit here to the right. I'm going to make this a little smaller so you can see this. So notice I've got the ramp there in red, and I'm going to draw my box. I'm going to make a black box here, like right here, something like this. Okay. And then the first thing I want you to notice is in green, I've already set up this coordinate system, and hopefully you're noticing something different from what we've previously done. Previously, we've basically made the x-axis horizontal to the ground, and the y-axis has been vertical to the x-axis, which means vertical to the ground. But notice what I've decided to do here is I've decided to kind of rotate the coordinate system so that it matches the angle of the ramp. And this is really key, and this helps us make this problem a lot easier. So let me just kind of walk through it and you'll see why. So we have done part A, okay? Part B, draw a free body diagram of the box, okay? So free body diagram of the box. So if the box is near the surface of the earth, it's going to experience its weight. So I'm going to draw this. You can see I have F sub G, okay? The other thing is we know that the box is pressed against a flat surface, that ramp surface. And remember, the normal force by definition always acts perpendicular to the orientation of the surface. So the normal force is going to act up in this direction, perpendicular to the surface, okay? And oftentimes I see students not draw it this way. They often draw it, say, this way. And you don't want to do that. You don't want to fall into that mistake, okay? Because that would be incorrect. So here is the normal force. And then the friction force. Friction force acts between the two surfaces. Remember, we always know that it acts parallel to the two surfaces. And since the box is traveling down the ramp, in what direction does the friction, the dynamic friction act? It acts up the ramp. So I'm going to draw it here, okay? But then very quickly here, I'm going to redraw this in a second to kind of show the trigonometry a little more easily. So as usual, we are going to reduce this box to a point particle, okay? And I'm going to do that right now down here, okay? And I'm going to redraw my axes really quickly as best I can. Excuse if they're not exactly perfect, perfectly linear. There we go. We got X. We got Y, and this is positive, positive, negative, and negative. Okay, and then my forces are going to be the force of gravity coming down like this. Got the normal force coming up like so. And we've got the force of friction looking something like this. All right, all coming from that particle. Okay, so we've drawn the free body diagram. Awesome. Now let's complete the forces table. So notice I have this table set up here. So we have some of the forces in the X direction, some of the forces in the Y direction. So here's where we got to really kind of evaluate the situation carefully. One other thing I want to note in the original problem is it tells me that this angle right here is 37.0 degrees. Okay. And so let's just talk about it right now. It's very important that we establish a relationship between this angle and this angle right here that I just outlined in red. And I'm not going to go through a rigorous mathematical proof, but you can imagine that if as the ramp angle diminishes, let's say as it goes from 37 down to 0, what happens to this angle here between the negative y-axis and force of gravity? Notice that that angle also shrinks to 0. And if we go in the other direction, if we made the ramp even steeper, that angle would be greater than 37 degrees. And notice that the angle between the force of gravity and the negative y-axis would also increase. So they track with each other. So again, what I'm going to ask you to do is kind of believe me, and if you want a more rigorous proof, I'm happy to offer you one, but this angle is also going to be 37.0 degrees right here. So that means this guy is 37 degrees, okay? So notice we have to, when we now go to this forces table, the forces in the x direction, well, notice I have two forces in the x direction. I have negative force of friction. I can put that one down. But I also have, and I'm going to try and draw this here, notice the force of gravity, part of the force of gravity is operating in the x direction. And the part that is I'm drawing it here in gray, okay? I'm going to call this FGX, okay? So I have FGX, the x component of the weight that is acting along the surface of the ramp. Okay, what about in the y direction? Well, in the y direction, notice we have the force normal that's acting in the positive y direction. And similar to FGX, I also have a portion of the weight that is operating along the y-axis, and that's FGY. And I've drawn it in gray here just to kind of differentiate it. Okay, and so again, in my forces table, I would write minus FGY. Awesome. Now we know something about the net force, okay? The net force in the y direction, as we've defined the y direction, the net force is 0, right? The box is not accelerating either in the positive y or the negative y direction because it's sliding exclusively down the ramp. And this is why we chose the coordinate system we chose, because then we can say it's 0 for the y direction, which makes this problem a lot simpler. In the x direction, we know there is some acceleration, so it's going to be m mass times the acceleration in the x direction. Or I could have written it as this if you're thinking, hey, why don't I write it like this? Yes, you could write it like that as well. But we know that this expression, x component of gravity minus friction, has to equal the mass times the acceleration in the x direction. That's Newton's second law. Awesome. Okay, so we completed the forces table. Now, let's figure out what's going on with the forces in the with the normal force. To do that, I'm just going to, again, just for illustration purposes, I'm going to very clearly draw this triangle here. I'm going to highlight the triangle that I'm talking about here. If you notice here, there's a triangle here that I can make, okay? I just highlighted it in yellow, and I'm going to draw it over here. And let's pick a color maybe that we haven't done yet. Actually, I'll go with gray. Okay, so notice I've got force of gravity coming straight down. And then this triangle here, notice it consists of two things. First of all, I have FGY. And then I have over here, remember vectors can be drawn in different directions, or like they can be moved, right? As long as you keep the magnitude and the direction the same. This would be FGX, okay? And this is FG. And so what I have here is a right triangle where FGX is coming down here. I add FGY is coming down here. I add FGX to it, and I get my resultant vector FG, okay? And this is a 37-degree angle here. Okay, so with that in mind, let's proceed with part D, because part D says what? Determine the size of the normal force. Okay, so we can use this equation to say the sum of the forces in the y direction equals the normal force minus the force due to gravity in the y direction equals 0. So the normal force just equals the y component of the force due to gravity. So how can I figure out the y component of the force due to gravity? Well, I have to go back to this triangle and I have to use SOHCAHTOA. Notice in this case, FGY is the adjacent side to this angle. So adjacent, so toa. Adjacent means I'm going to use cosine. So what I can say here is that the cosine of 37 degrees equals FGY over FG. Or in other words, FGY equals FG cosine 37 degrees. So that means the normal force equals FG cosine 37 degrees. And we know the object's weight is just going to be its mass times the acceleration due to gravity times the cosine of 37 degrees. So when I substitute in those values, the mass is 4 kilograms. I'm told to use 10 meters per second squared for this problem, just trying to keep numbers simple while we grapple with new concepts. Cosine of 37, what is the cosine of 37? It is 0.79 or 0.8 basically. So what I get here is I get that the normal force is 32 newtons. So now I have my answer to part D, 32 newtons. And so notice it's just part of the overall weight, right? Which makes sense. Okay, let me just make sure we understand where this came from. Yeah, all right. So we've done part D. We're 4/6 of the way there. So let me put a box around part D, just so looking back on this, you can get a better sense. There's part D. All right, now let's go to part E. Part E says determine the size of the dynamic friction force on the box. Okay, so for part E, we want to know what the friction force equals. Well, remember, friction force equals the coefficient, in this case, dynamic friction, times the normal force. Well, we got the normal force in part D, so this is quite simply taking 0.25, multiplying it by 32 newtons. We get an answer of 8.0 newtons for our friction force. Hey, that wasn't so bad. Awesome. Okay, so we've got part E done now as well. Finally, part F, determine the acceleration of the box. Okay, this one can be tricky. By the way, let's go back up to the free body diagram. I suspect there are at least a few of you out there who said something like, hey, wait a second, Mr. Bob, shouldn't there be a force down in the direction, down the ramp, that's pushing it down, that's causing it to accelerate down? And the answer is there already is in this drawing, so you don't need to draw an extra force. Because why? Because that force that's pushing it down the ramp is just the x component of the force due to gravity, right? If you didn't have the ramp, if the ramp was flat, there would be no acceleration, okay? So, so when we get to part F, what we can say, do I want to do part F? No, I'm going to do part F in gray. Part F, we're going to use this right here. Say that sum of the forces in the x direction equals Fgx minus the force of friction. And in this case, it equals the mass times the acceleration in the x direction, because we know there's acceleration. So I'm asked for the acceleration. So what do I need to do? I'm just going to rewrite this here. Minus force of friction equals max divided by m divided by m. The acceleration in the x direction is going to be the difference between that x component and the force of friction divided by the mass. Now let's go back here. How do we get the x component of the weight? I have to go back to this triangle over here. Okay, and now I'm looking at this side. This side is opposite the angle, right? So opposite hypotenuse, I would use sine. And so let me just very quickly over here do an aside to say that the sine of 37.0 degrees is going to be equal to what? Fgx over Fg. That's what my triangle shows me. So when I solve for Fgx, that's just Fg sine of 37.0 degrees. And again, we know that Fg is mass times the acceleration due to gravity. So in other words, mg sine of 37 is going to equal our x component. And let me just substitute in the values here. 4 kilograms, 10 meters per second squared. Sine of 37 is 0.6, I believe. Yes, 0.6. So what do I get? I get that the x component is 24 newtons. So now I can go here and I can substitute in here 24 newtons for my x component of the weight, force of friction is 8.0 newtons, and the mass is 4.0 kilograms. All right, let me just kind of cordon this off. And so I get 16 over 4, or the acceleration is determined to be 4.0 meters per second squared. Okay, so let's kind of review some really important things about this problem before we finish up this video. One is selection of the coordinate system, right? Coordinate system, we had to basically make it match the incline of the ramp. That's key number one. Key number two is draw our force vectors correctly. Weight is still pointing straight down, and normal force is still perpendicular to the surface. And so now they're not directly opposing each other. They're at an angle. The other thing to remember is our friend SOHCAHTOA, and the fact that this angle here, this ramp angle, is also the angle between the weight vector and the negative y-axis. That's always going to be true, always, always. The ramp angle is the same as the angle between the negative y-axis and the weight. And then drawing this triangle correctly is really key, and something I see sometimes students mess up on. The rest of it just really relies on things we've already learned and building on those skills. I hope you enjoyed this video, and I look forward to working with you on this in class. Thanks, everyone.